All right, folks, so today we're going to talk about relations and functions, the difference between those two terms. We're going to talk about some function notation, how to use f at x and f of x, and we're going to talk about how to tell the domain and range of a function, what those two words really mean. We're going to start off by talking about here the number system that we work in and the number system that we're going to work in as we work through this course. So you are used to working in the real number system, and that's also called the reals. And that's denoted by a short form R. Now the real numbers are a subset of the complex number system. So that means all real numbers are part of the complex number system, but not every number in the complex number system is a real number. Okay, so because there are imaginary numbers, what we call the number I, and all of the numbers in the imaginary number system, those ones we're not going to be using in here. Now the real numbers themselves, that is one subset of the complex number system, but we can break those numbers down even further. So we could break those down into irrational numbers. You may have heard of some irrational numbers before. That would be a number like pi, or like the square root of 2, or like the number e. And I do know some of those. I believe e, I don't think you have worked with yet before, but you may have seen it on your calculator. Those are numbers that are irrational. That means the decimal keeps going on and on forever. It does not repeat itself. Otherwise, we have the rational numbers, and those are numbers that can be shown as part of a fraction. So that means if we have 2 over 3, that's a rational number. That is a number that you're definitely used to working with. Then we have the natural numbers, and the natural numbers are also called your counting numbers. So that's like the numbers 1, 2, 3, etc., and so on. Those numbers you are used to using, but you'll note that some numbers are not included in there. Those numbers that are not included in there that you are used to working with, like the number 0. So the number 0 with the natural numbers here, that makes up our whole number set. Additionally, you have worked with integer numbers, and integer numbers will include your whole numbers and include your natural numbers, but they'll also include the negative values. So -1, -2, -3, etc. In the negative direction. So your integers are a larger subset of numbers than your whole numbers. Your whole numbers have more numbers in them than your natural numbers, just because of the differences I have pointed out here. Also included in here would be repeating terminating decimals. So something like a repeating decimal would be 0.191919, and that goes on forever. Or terminating decimals, rather, would just be something like the number 0.191. That's a terminating decimal. Now, we're going to, now that we have our basis, the numbers that we're going to be working with in here, you'll see how that comes up a little bit more when we start talking about the domain and range of functions. But I'd like to keep going here. So we would consider the following displays of y equals x squared. And that's our base quadratic function. You've worked with quadratic functions before. You spent a fair amount of time in grade 10 working with quadratic functions. So first of all, we're showing the quadratic function here with a table of values. You have used table of values for a number of years here. We will be using them in this course. That's where we'll list off, say, all of the x values in one table, and in one column, and all of the y values in another column. And we'll note that the values go together if they're in one row. So if we were to put this, say, on a graph, and this is a graphical representation, say we were to put these on a graph, this first point would be the point -2 and 4. So that would be 1, 2, -2, and it would go up to, it'd be -1, -2, and it would go all the way up to 4. So this point, -2, 4, we can see that it was in the table of values. It's on our graph, so we can tell as well that these are representing the exact same function. You also have used before, maybe you haven't used them as much, but a mapping diagram. And a mapping diagram will have, say, all of your x values, your independent values here, all of your y values, those are your dependent values here. And we can see that y depends on x because of this arrow going across here. Again, so this -2, 4 point, you can see them go together. They have an arrow connecting the two. That's like your input is x, whereas your output value is y. Moving forward, we have one more way here in which we're going to talk about where we can represent a function, and that is with a set of ordered pairs. And in terms of the set, we can see that the set begins with a squiggly bracket here. It ends with another squiggly bracket. That's how we will get used to defining a set, and you'll see what I mean by that when we start talking about domain and range. Again, that will be a common theme, but you can see that these ordered pairs are always showing x and then y. You've been using that pattern for a number of years. I'm not sure how familiar you are with the term, but these are ordered pairs. And again, we see the same point coming up to, -2 and 4. Now in math, when we have a single output for a given input, and that's important, a single output for a given input, we see that's what we have up here. So for each input, -2, there's only one output, right? Input -2, output 4. There are not multiple outputs for that one input, and that means for each x value, there's only one y value. When we have that, we say that we have a function. We're going to call a function a relation in which each element, of the domain, and that's what we're going to talk about today. Domain is x, so each element of x is paired with exactly one element, not more, of the range. And the range is y. Now a relation a function is a relation in which each element of the independent variable x, so the independent variable, those make up your domain, corresponds to only one element of the dependent variable. That's your range here. Now note here, all functions are relations, but not all relations are functions. That means that a function is a type of relation. Okay, so that's how we're going to work. Now we can represent a function or a relation graphically, and you saw that up above. Numerically with a table of values or a mapping diagram, which again you saw up above, or algebraically with an equation. And this up here was shown with an equation initially when we were given it y equals x squared. If we see an equal sign there, then we know we're working with an equation. The domain and range, those are terms that we'll use to describe the sets of all possible x and y values of a function or relation. So that means your domain is going to describe, your domain is the set, again, set is maybe a new term, but you're hearing that theme a lot as we go through, the set of all x values, which again are your independent variables, is your independent variable rather, included in the relation. Whereas your range is going to be the same thing, but for y. So it's going to be the set of all y values, and this time that's our dependent variable, included in the relation. Meaning your domain is all possible x values that your function takes on. Your range is the same thing, but for y values. All possible y values. Now let's take A look at the example. Again, we're going to work with our quadratic function, y equals x squared. That's our base quadratic function. We know the shape of that. We're used to working with that. So let's talk about it. Well, we know that our base quadratic function, we know what that looks like. Let's just do a quick drawing here. Our base quadratic function. There we go. Let's move that over. Oops. Perfect. Our base quadratic function looks something like this. And we'll label that y equals x squared. We know the shape of it. Now, if we take a look and if we analyze this a little bit further here, so note that we have our x-axis that's working horizontally here, our y-axis that's working vertically, and we can just note the different locations that our function takes up. So remember, the domain is our set of all x values in the real number system here. That means that when we're working with our when we're working with our base quadratic function, that means that all of the input values it can handle are any value along the real number system. So our x values that are possible to go in here, all of our possible x values, there are no limitations on them. We can handle any x value. We could square that x value, and that would give us an output value for y. So it's all, again, all x values in the real number system. So the way we write that, we open it with a squiggly bracket here, x values that are elements of the real number system. Again, this r represents the real number system. The little e here, the epsilon, that represents element. That's what it means in English, if you will. Now, note the difference between the domain and the range here when we're working with our quadratic function. We note that all of, again, we're expecting to be able to handle every single possible x value. But when we're looking at the y values, that's not the case. We can see that this entire part of the graph, the graphing area, is untouched by our function. We don't have any points on this function that will have a negative value in terms of their y coordinate. So here, our range is the set of all y values in the real number system. Again, we're working in the real number system, such that y is greater than or equal to 0. And that means that we're not going to be considering y values less than 0, because it's not possible to come up with a value, no matter what x is, y will never be less than 0, because we're squaring x when we're calculating for y. So that means the way we're going to write its range will be y is an element of the real numbers, such that, that's what this vertical bar means, such that y is greater than or equal to 0, and then we'll close the set there. So we call this set notation to describe the domain and range. That's how we're going to describe our domains and ranges, so that others can read and can tell what we're saying here. Now, if we're translating this to English, let's take a look at this domain here. That means that, like I said out loud, x is an element. That's what our epsilon symbol means there, an element of the reals. And again, reals is kind of a shorthand for real number system. Let's take a look a little bit further. Let's take a look just at the next example here. So we're going to consider these relations, and we're going to decide whether or not they are, in fact, functions. Remember, we have our definition of a function that we came up with at the bottom of the previous page that tells us a function is a relation in which each element of the domain is paired with exactly one element of the range. That means for each input, there's only one output. So here, if I see a table of values and I don't see x repeated anywhere, and I don't here, I see -3, -1, 0, 1, 2, 5. There's no repetition there. So because there's no repetition, then I can be quite sure that there's only one y value for each of these, and that's the case as shown by the rows here. So negative 3 has one y value. Negative 1 has its own y value. X has its own y value. So the domain here, so just from telling that, then we can say it is in fact a function. And if we look at the domain here, we might notice a pattern, and that's fine, but the way in which we stated our domain before, where x is an element of the reals, we don't necessarily need to say that because we're actually given all of the x values here. So the domain that we're working with is going to be just a list of all of those possible x values. Remember, domain means all possible x values. So here our domain is negative 3, negative 1, 0, 1, 2, and 5. And it is a good habit to always list your domain from lowest to greatest, so that's what we're going to do here. Now the range is also shown here. That's all possible y values. Well, we can state that in the same manner, just listing them off. Negative 11, negative 8, 0, 4, 7, and 9. Next, let's look at one using a mapping diagram. If I look at my domain and range, we'll start off there this time. My domain, again, is all possible x values. I know that my x values, my input values, are here on the left. If I don't remember that, I can see that the arrows are going from left to right. That means for this input, there's that output here. So my domain here would be all of the numbers 5, negative 2, and negative 4. Again, we're going to write that in from least to greatest. So negative 4, negative 2, and 5. And my outputs are negative 6 and 8. And if I look here, I might be tempted. Let's see. If I take a look just at the first one here, I can see that 5 as an input goes to 6 and it goes to 8. Because it goes to two things, that tells me that this is not a function, because that means that there are two outputs just for that one input. Now note, I am allowed, if I have a function, I'm allowed to have two inputs go to the same output. There's no problem there. But what makes this not a function is that the fact that two arrows come out of this single input term. Okay, so this is not a function here that we're looking at. Now, if we're looking at a graph, we can't necessarily list off all the time all of the terms that we're considering. But we do have a way of checking to see if if a relation is a function or not, and that's called the vertical line test, wherein we work with a line here. Let's see if I can select it. Nope. We work with just one line, and we consider this line being pulled across our function. So if we were to keep drawing our line across the function, we should be able to see if our line is crossing the function more than once. If it ever is crossing the function more than once, then the entire thing is not a function, it's just a relation. Okay, so on this first function, and let's choose a better color than blue here, just so we can see. Let's look with red. So this first one, if I keep drawing vertical lines across here, our vertical lines only ever touch the function one time. One time. So we'll call this one a function, because we'll say it passes the vertical line test. Now, the next one, though, if I'm to draw my vertical lines in, first, I can draw a vertical line. It touches the function in 1 point, just 1 point, so it's passing so far. But if I move that vertical line over just a tiny bit, I can see that it touches the function twice. And it's a vertical line. It's straight up and down. It touches the function twice. So it fails the vertical line test. This is not a function. And then we're going to look here. We call this a stepping pattern. If I see a closed circle, that means that the function goes all the way up to that point, all the way up to that circle, and then it stops. It goes no further, but it includes that circle. Otherwise, if I see an empty circle, it means the function goes all the way up to that empty circle, but it does not include the actual point of the circle. So an example, if a circle went from, let's see here, if our line goes from, we'll call that negative 8 That's just a guess, and negative 4 here. Then negative 8 would be, if I look at where x equals negative 8 and y equals positive 3, that would be on my function, yes. And it would be on my function for all values from where x goes from negative 8 to negative 4. It would still be on that function until I'm actually looking at the point negative 8, negative 4. That's not on the function. If I go to negative 4, 1, 2, 3, 4, if I go to where x equals negative 4, then actually the function equals negative 1 shown down here. If you're confused about that, that's okay, but really what I want you to realize is what the filled in circle means and what the empty circle represents here. Now, if I consider my vertical line test, I can use my vertical line everywhere. My vertical line is touching the function twice at a quick glance, but if I look a little bit closer, I can see that my top circle is empty. That means the function's not actually there. The function's down here. So far it's passing the vertical line test. I can keep drawing. It only ever crosses the function once at a time, crosses the line once at a time. Therefore, we do have a function here. Now, in terms of these graphs, we can just get a little bit of practice stating domains and ranges as we're working here. So for the first graph here, our domain, and let's erase all of the notes I've been putting on here so we don't get mixed up. Our domain is any possible x values involved. Well, if I zoom in here, then I can see an arrow at the end of each line, and that means that the function will keep on going even though there's no more room on this graph. So if the function keeps on going in that pattern, then I can see that all possible x values are going to be used when talking about this function. So my domain here for this function would be x is an element of the reals, and there are no restrictions here. So I'll close my set there. X is an element of the reals. All possible values of x here could go into this function. But in terms of the range, if I were to say mark all of the y values that are involved on this function on the y-axis, then let's say even if I start all the way out here, that would be on the y-axis there. And that would be true until here, and then I could see it would be on the y-axis all the way up. And that's it. There are no points on this function that have a y-coordinate that's any higher than this or any lower than that. So we would need to consider, okay, well, whatever those heights are, and we'll say that's positive 5 and negative 3 down here. That means that we call this an upper bound. Negative 5 here an upper bound. We call negative 3 a lower bound. That means that there are no values less than that we're considering here. So when we state the range here of this function, it would be y is an element of the reals such that, because again, we're going to use this such that symbol because we will have a restriction. So such that, and then we state the restriction. Well, negative 3 is going to be our lower bound, and our function is allowed to equal negative 3. So we'll have our y value is allowed to equal negative 3. So we need a less than or equal to sign. So negative 3 is less than or equal to y, which is less than or equal to 5. That's the end of our restriction. So we'll add a closing bracket here. And that's going to be the way, this is going to be the strategy we use to represent our domains and ranges if we're working with a function that is continuous. And you'll see what I mean by that term as we keep going in this lesson. But basically, it means if you're seeing a solid line here in the graph, then we're going to be using x as an element of the reals or y as an element of the reals to describe the domain and range that we're working with here. Now let's move on to the second graph. And here we're going to state our domain first. All possible x values. So that would be, this looks like negative 3, where x is here. Looks like there's a negative 2. We have two values here. Sorry, not for this function, for this relation. We have two x values at negative 2 and two coordinates, 2 points, 2 data points on a relation at positive 1. And two of them again at, it looks like 1, 2, 3, 4, 5 at positive 6. So we'll say here that the domain is, and again, we'll go back to that listing strategy. Our domain goes negative 3, negative 2, positive 1, and 6. And it can only take on those values. You'll notice there is nothing drawn on this function relation. There's nothing drawn anywhere in between, say, -1 and 6. There are only data points at -1 and 6, and that's why we're going to show our domain in this manner. We're going to look at it at the range in a similar fashion because there are only a certain number of data points here. All of the possible ranges are, let's see here, 1, 2, are -3. That's where this one lies. -2, -1, 0, +1, +2, and +3. So our range, we would say we could list in one of two ways. One of which is to list them off. So our range is -3, -2, -1, 0, +1, +2, and +3. And the other way we could describe our range would be to do so using a different number system than the real numbers. So if I were to look at my range, I could say, okay, well, y is an element of the integers. That's a symbol that means integers. Y is an element of the integers such that -3 is less than or equal to y, which is less than or equal to +3. And lastly, let's take a look here at the third function. The third function, if we look at the domain here, we'll notice the domain. We do have a function for all values of x that are, let's see, -1, 2, 3, 4, 5, 6, 7, 8. It goes from -8, looks like, up to +8, I would say. 1, 2, 3, 4, 5, 8. That's right, up to +8. So our domain is going to be, again, because we have a solid line, we have this solid line here, so we'll write our domain in terms of the real numbers. So x is an element of the reals such that, and then we look at the highest number and the lowest number that's involved. The lowest number is -8. -8 is less than or equal to, x is less than but not equal to 8, because we notice our function here does not keep going all the way to the number 8. It just goes up to, but not including the number 8. So that's our domain that we're working with, whereas our range here has only discrete values. It has only certain values and not the values in between. So if we see here, we would have to count down. Let's see. Looks like our first value is +3, and then -1, and then 1, 2, 3, 4, -5, and -9 here. So our range that we're working with here, we need to list it off. We cannot just say that y is an element of the reals. That's not good enough. Here we need to say, okay, y can range from -9. It can be -9, -5, -1, or 3. Those are the only possible y values involved in this function. Now, that's a good start. Here we're going to talk a little bit further. I know we're going into a lot of detail here, and that's fine. This is almost all of the lessons that we do cover on this first day, so don't sweat it if this feels like a lot of information. It's just all going into one video today. That won't be the case all the time. Now let's look here at algebraic representation, at another algebraic representation, and that's using function notation. Now you have been using y equals something in order to represent your functions as you've been in grade 9 and grade 10. Now in that case you're used to saying, say, y equals mx plus b if you're in grade 9, or y equals x squared, or a different version of that if you're in grade 10. Well, now we're no longer going to use y. Well, sometimes we'll use y, but often we won't. We'll get more used to working in function notation here. So, and we're going to look at this. It's basically going to replace y often in our variable, or in our equations. So here we can have our standard linear function, and we replace the y with an f at x. We write that as an f and then a bracket and then an x in brackets, sorry. And that means we read that out as f at x or f of x, whichever you prefer. And here we cannot confuse this with an f times x. We are not multiplying f times x here. Although that's what brackets usually represent in mathematics, this time they do not. In this case, they just mean our function evaluated at x value. Okay, our function evaluated at the value x. So you'll see our quadratic function here. Instead of what we're used to seeing, y equals x squared, now we write f at x equals x squared. These are our base functions. These are going to be the base functions that we work with throughout this year. This is most of them. We have here a linear function. You've seen that before. You've seen a quadratic function before. And you should have, I suspect you've seen some cubic functions before. We also have what we call the absolute value function, our exponential function, our reciprocal function, our square root function, and a sinusoidal wave, and that's this one's our sine function. Now, we don't need to memorize those at all. We will become far more familiar with these functions as we work through this course. Let's take a look at the first example using function notation here. So remember, f at x means f evaluated at x. If that's the case, then f at 0 means f evaluated at x equals 0. So we can write f at 0 equals, and we'll write in this f at x, 3, but instead of writing an x, because again, here this is like saying f at x equals f at 0, so x equals 0. That means that f at 0 would equal 3 times 0 minus 1. 3 times 0 is 0. We're going to follow our BEDMAS here, our order of operations. 3 times 0 is 0, leaving us with f at 0 equals negative 1. That's how we would say this. You might be tempted, and I saw some folks in my class earlier this week, they were tempted to try and isolate for this f. That's not what we do here. Remember, the f is stuck to that to the bracket 0. This means f at 0. The f is completely meaningless without something in its brackets beside it. So in this final form, then we write f at 0 equals negative 1. We don't necessarily need to write it that second time because we have our equal sign there. Now, here we're working with an f at x, and we're also working with a g of x. Now, note, we can use any letter that we want. We're going to use them strategically so that other people can understand what we're writing, but we can use any letter that we want to represent a function. So now, if we're ever working in a question where we have more than one function, we're just going to choose another letter. So in this case, it's g. So we're going to evaluate g at 3, and that means we're going to evaluate g of x where x equals 3, so we can fill that in. Instead of writing the x here, we're going to write the 3. So we're taking it from here. Instead of writing the x, we write the 3, and then we square it. So 3 squared equals 9. That means g of 3 equals 9. Now, if we have an f at x or an f at a certain value, or a g of x or a g at a certain value involved, it's not always going to be isolated. So note here, what we have is we have the number 3 multiplied by f at 1. Still, the f at 1 we're not allowed to separate. That needs to be stuck together, but there's a 3 beside it, and we're going to work with that. So this is 3 times f at 1. Well, f at 1 is from our f at x over here. Oops, squared. Our f at x over here. So f at 1 equals 3 times 1 minus 1. We'll close that bracket. So that's 3 times 1 minus 1. Again, we're going to follow our BEDMAS here. That's 3 times 3 minus 1, which is 3 times 2, which is 6. So that means that, and again, we're just evaluating here what's going on. So that means that 3 times f at 1 equals 6. That's our final answer. That's what we were asked to find. And lastly, we were asked to find f at 1 minus 2 times g at 2. So that means we need to evaluate here two things, f at 1 and g at 2, if we're going to be successful. Let's try it out. F at 1, I know how to do that by now. That's 3 times 1 minus 1. And again, I got that from the beginning here. Minus 2 times g at 2. And again, I'm going to get this from the beginning here, g at x, except I'm going to replace that x by a 2. So g at 2 would be 2 squared. Again, we'll follow our BEDMAS here. 3 times 1 minus 1, That's 3 minus 1 when I'm evaluating my f, minus 2 times 2 to the power of 2. That's 4. And if we simplify that even further, that brings us to minus 2 times 4, which is 8. So 2 minus 8 is negative 6. Lastly, let's evaluate x if f at x equals 9. So note here, we're not told a certain value that x is. We're just going to, we need to find that for ourselves. So if we know f at x equals 29, well, I know what f at x equals. F at x at the start, I'm told f at x is 3x minus 1. So that means that I can take out the f at x and I can write in 3x minus 1. So if 3x minus 1 equals 29, then I can isolate 4x as you have done before. So 3x, I can add 1 to both sides. That brings us 29 plus 1. So 3x equals 30. And I can divide both sides by 3 to isolate for that x. So x equals 30 divided by 3. 30 divided by 3 is 10. So x equals 10 if f at x equals 29. These are questions very similar to ones you've handled before. In fact, the same as ones you've handled before in previous versions of math class. The only new thing is the terminology and the notation. Now we're using f at x rather than writing 0. Okay, we're getting there, folks. We're nearly finished. We're going to evaluate a few more. Let's say f at x equals 2x minus 5. Then if I'm evaluating f at 1, again, I'm replacing the x with a 1. So that equals, let's see here, 2 times 1 minus 5. I can use my BEDMAS. That's 2 times 1 is 2 minus 5, which equals negative 3. We can perform the same thing here if even if x is a negative number. So f at negative 3, well, that equals 2 times negative 3 minus 5. Okay, 2 times negative 3 is negative 6 minus 5. Negative 6 minus 5 equals negative 11. And moving on, if I'm evaluating 2 times f at 5, then I'm going to use my square brackets here. 2 times f evaluated at 5. So f evaluated at 5 is 2 times 5 minus 5. Close my brackets. We'll follow our BEDMAS here. That's 2 times 10 minus 5. Again, brackets first. That's 2 times 5, which equals 10. And I'm going to leave example 3. Actually, you know what? Let's try it out. In particular, B is going to be new for you. So let's just jump to B. I'm going to leave A for you to do if you did miss the first class. Let's try this out. This time for B, and instead of writing my equal sign beside, I'm just going to write it underneath. We're allowed to do that. It's just depends on the way you like to write this. So this time we're going to evaluate f, and here we're told what f at x is. We need to evaluate f at where x is x plus 1. So instead of writing x under f at x, now we're going to write x plus 1 anytime that's there. So that tells us that we're working with x plus 1 squared instead of just x squared. And we're going to add that to 3 times what used to be x and is now x plus 1. And then minus 2, there's no x involved there, so we leave that as is. Now here, we're going to use what we call our distributive property here. It's we're going to use FOIL. So x plus 1 squared, well, if I expand that out, that's like x plus 1 times x plus 1 plus, and here I can use my distributive property to multiply my 3 into those brackets, so plus 3x plus 3. That used to be in the brackets, minus 2. All right, we're getting there. Here we're going to use FOIL. We have 2 binomials, so that's 2 pairs of brackets with 2 terms in them. We're going to multiply the first terms by each other, and that's what the F stands for, is first. Then we're going to multiply the outside terms by each other, and then the inside terms. And lastly, we multiply the last terms by each other. So the first ones are x times x, and that gives us x squared. And then the outside terms, which are x and 1, are going to give us a 1. The inside terms are x and 1 again, so that gives us an x. And lastly, last times last, which is 1 times 1, which is 1. That's how we distribute when we have two binomials. And then we'll keep going, plus 3x plus 3 minus 2. Good. Now, at this stage, because inside the brackets I only have terms being added together, I no longer need my brackets there, and I can remove the brackets and I can start to collect my like terms. So my first term is x squared. There's only one term with an x squared, so we'll write x squared here. And then I have many terms with an x, so plus x plus 3x, all there, so plus x plus 3x. And lastly, I have a plus 1, plus 3, and minus 2. So plus 1, plus 3, minus 2. And if I simplify that, if I collect my like terms, so that's 3x's plus x plus x. In total, that's 5x's. Then over here, I have 1 plus 3 minus 2. Well, that's 4 minus 2. That's just 2. So if I am to evaluate this, yes, it's a lot of lines. That's going to be math sometimes, but in this case, we would evaluate it to be x squared plus 5 plus 2. Now I'm going to leave these two for you here. They're challenge questions. I'd like you to try them out, see how it goes. And otherwise, let's finish this off here. I told you we would tell the difference. I would explain the difference between a discrete relation and a continuous relation. A discrete relation, well, that's shown by points or a dashed line. Now a dashed line, sorry, so these are shown graphically by points or a dashed line. So we can see here a point, a point, a point, there are 4 points, and then a dashed line going about, and that means that the pattern will continue in that way. But it's not the solid line we're used to, which would mean that there's a data point everywhere on the line. Because it's a dashed line, it means the pattern continues as it was. So the number set that's represented by these examples down here is the integers, and we have worked with the integers before. The short form for this set is an I with two vertical lines, is a Z with two diagonal lines. A Z with two diagonal lines. I think actually I used the wrong symbol up above when I was doing that. That's right. I wrote Y as an element of the integers. Should be like that. Perfect. Now, if we're looking at the domain of a function like this, so we're going to try and interpret these graphs. If I look at the domain, I'm going to look at all possible values of x, right? And in this case, because this is discrete, then we're going to use, and discrete meaning it only uses certain values rather than all of the values within, from a certain number to another number, in which case we would be talking about the real numbers. Here we're just talking about integers. So that means we're talking about the number -1 and the number 0 and the number 1, but we're not talking about the numbers in between. So for example, we're not talking about 0.5 or -0.5, and here we're only talking about the integers. So our domain can be given by x is an element of the integers this time, not the reals, by the integers, such that x must be greater than or equal to -1. And that's our -1 that we see right here. We always do the closing bracket to finish off the set. Now about the range, well, what are all of the possible y values here? There's only one possible y value. They all share the same point. All the data points share the same y coordinate, and that's a +2. So that means that our range is just +2. That's it. It's nice and simple. It won't get any easier than that. Let's take a look at this other one here where we can see, okay, there is no dotted line. There is no dashed line, meaning that these are the only 4 data points here. Okay, there's no dashed line. There's no solid line. These are the only 4 data points. So if I take a look here at the domain, those are the possible x values. Well, this has an x value here and there and there and there if I look at all of them. So that means that my domain is going to be 2, 3, 4, and 5. All right. Now if I look as well here at my range, well, that's the y coordinate of all of these points. And that looks like it goes, oops, that's not the straightest line here. that looks like it goes 1, 2, 3, and 4. So my range is just going to be that 1, 2, 3, 4. Close the set, and that's it. It's that simple. Okay. Now, a continuous relation, these are the ones we've been working with. These are the ones you're used to working with. These are the functions that you know what you're talking about. These are represented by a solid line. And that's just like when you've used before a quadratic function, right? We draw that in as a solid line, not a dashed line, or a linear function, where again we draw it in as a solid line, not a dashed line. So the number set represented by by continuous relations is the reals, and that's the one that we have been working with. The short form for this has two vertical lines in the R, in the capital R, and examples of continuous functions. An example of a continuous function is the quadratic function. Other examples of discrete functions would be our list of functions that we went over on the second page here. Oh, you know what? Maybe it was on the first page. Maybe I lost it. That would be like the linear function, the quadratic function, the cubic function, the square root function, the exponential function, and so on. Now, I'm hoping that this video helped you. If you have questions about it, don't be afraid to reach out. Thanks.